Sorry, so in that last video, it accidentally stopped recording, so it didn't get the answer for you. The answer was 226.195. So make sure you got that, and then we'll move on to the next example. Okay, so here's another one. We're still dealing with the same shape, y equals 2x, bound by 0 and 3 for y equals 0, x equals 3. This time we're rotating around the line y equals 8. So let me go ahead and sketch this really quick. One, two, three, four, five, six. Alright, so there's my shape. Remember, it's this area. Only this time we're rotating around the line y equals 8, which is way, way, way up here. So if I reflect this over that line, now it looks like this. So notice that now my shape doesn't even touch this this other function. And so if I draw my inside circle and my outside circle, the outside still looks cylindrical like it did in the last example. And the inside does look conical still, like a cone, except for the fact that it doesn't come to a point at the bottom. It kind of comes to this. So if I did rotate this around, it is a solid shape in the sense that from the outside, if you're looking at it, it looks like a cylinder. But from the inside, you can actually see all the way through it, and there's a hole in both ends. The hole at the top is a conical shape or a cone shape, very, very wide, and then at the bottom, it's still this circular cone. It's just that it spits out the other end of the bottom, and it doesn't actually come to that point or that tip at the bottom like it did in the last example. So our outside radius for the red function is represented by this red line right here. Remember, top minus bottom. So the top function in this case is y equals 8, because this is the line y equals 8. So 8 minus the bottom function, so 8 minus 0, it goes all the way down to the x-axis, 8 minus 0, which is just 8. For the inside radius, the green function, that's this little green line right here. The top function is 8, and the bottom function is the function I'm working with, 2x. So this is 8 minus 2x. Now I'm going to go ahead and jump straight into our little shortcut way to write it. I'm not going to show how both of the areas are written out over here and how we can write out that big long integral like we did in the last example. I'm just going to jump straight to the volume formula. So remember, it's pi, because these are circles. The lower limit of integration is still 0. The upper limit of integration is still 3. And then it's the outside radius squared, 8 quantity squared, minus the inside radius squared, 8 minus 2x quantity squared, dx. And again, these come from the areas of these circles. Pi times the outside radius squared would be the area of this red circle. Pi times the inside radius squared would be the area of this green circle, and then the integral is adding together all of those areas for us to create this volume of this shape that we have. Go ahead and pause your video and see if you can put this in your calculator on your own and see if you get the same answer as I do. Alright, so I got 339.292 for the volume of this shape when you revolve it around the line y equals 8. Next, and we still have 3 more examples we're going to do with this shape before we move on to a different shape and what it looks like when we do it a little differently. In example D, so same shape, I'll write it again. 1, 2, 3, 1, 2, 3, 4, 5, 6. So it's still this triangular shape. Only this time we are revolving it or rotating it around the y-axis. So when you reflect it this time, I want you to reflect it across the y-axis. So, if I actually draw my inside and outside circles now, notice that if I rotate this shape around the y-axis, I'm creating a cylinder on the outside. Notice that it's still straight on the outside, so the outside shape creates this cylindrical shape. And then on the inside, it comes to a point in the middle. So it's like this cone shape, kind of like it was in the last example, or 2 examples ago, I should say. The only difference is that in this case, it is filled in again. So it doesn't go all the way through. It doesn't have a hole at both ends like it did in the last example. It's a wider version of example B in the sense that we still have this cone cut out of our cylinder, but it's a wider cone than before. So if I draw my outside circle, it looks like this. My inside circle looks like this. So again, these are washers because they have pieces cut out or volumes cut out from the inside of them. Now, notice that this one is a little bit different because no longer are we rotating around horizontal lines like we were in that first example. Now we're rotating around a vertical line. So we're going to write down in just a minute that when we rotate around vertical lines, everything has to be in terms of y. Everything has to change to be in terms of y. Which means that all of my limits of integration need to be in terms of y, all of my functions need to be in terms of y, my integral needs to be in terms of y, everything. So, whereas before we were looking at integrating in terms of x. So for example, my limits of integration were from 0 to 3. Now that we're rotating around a vertical line, I'm going to no longer look from left to right, I'm going to look from bottom to top. And my limits of integration will be from bottom to top. So the most southern point in my volume, or the lowest point in my volume, is at 0, y equals 0. The highest point in my volume stops right up here at y equals 6. So my new limits of integration are going to be from 0 to 6, so that everything is in terms of y. So let me get started down here with my volume formula. It's going to be pi times the integral from 0 to 6. Now, my function needs to be in terms of y. Currently, this equation is y equals 2x, which is in terms of x. I want to change that. So I want to isolate x and solve for x. To do that, I would divide both sides by 2. Therefore, x is equal to 1/2 y. Excuse me. So now I have an expression for this function in terms of y. X equals 1/2 y. So when you're doing these problems and you're trying to figure out the radius, because that's what we need to do now, is we need to figure out the expression to represent the radius of the red circle and an expression to represent the radius of the green circle. When you're figuring out the radius when you're revolving around a vertical line, I like to tell students to tilt their head. So right now when you're looking at your computer screen, go ahead and tilt your head to the right. So you're looking at it as if this is the top. So where my finger is pointing right now, if your head is tilted to the right, this would be the top, and this would be the bottom of the radius. And let me draw it in. So that red line that I just drew, you can see that, again, tilting your head, here's the top of that red line, and here is the bottom of that red line. So that's going to help us to write the expression for our radius. The top of this red line is touching right here, and this is the line x equals 3, so I know the top function is 3. The bottom of this red line is touching right here, and this is the line x equals 0. So the top function is 3, the bottom function is 0, and so the outside radius for this red line is 3 minus 0. Or just 3. For the green function, let me draw in the radius for the green function. Alright, so again, tilting your head to the right, notice this green line that I just drew in. So for the hollow part on the inside, the part I need to take away or get rid of, the top of this function is this line right here, and the bottom of this green line is 0. So this function, it used to be called 2x when everything was in terms of x, but now that we're changing everything to be in terms of y, I no longer want to call this function 2x, I want to call it 1/2 y. So the top function here on green, this is the line 1/2 y, and the bottom function is 0. So if I want to find an expression to represent the height of this green line, it would be 1/2 y minus 0. Or just 1/2 y. And now the equations are the same as before. The area of the red circle would be pi r squared with the outside radius. The area of the green circle would be pi r squared with the inside radius. We're going to subtract them. So I have pi. My limits of integration are in terms of y from 0 to 6. Then I have the outside radius, which is 3 squared. So again, pi r squared minus the inside radius, which is 1/2 y squared. Again, pi r squared, so I'm subtracting the two areas, and then dy. So now I have my limits in terms of y, I have my functions in terms of y, and I have my integral in terms of y. Pause your video and put that in your calculator. Remember, when we put it in our calculator, you would put it with x's in there because your calculator knows how to evaluate x's, but it means the same thing. And then push play when you're ready to check your answer. I put that in my calculator and I got 113.097 as the volume from when I revolve this around the y-axis. All right, let's try this 2 more times. I know it seems like a lot to do this over and over again, but when you guys see the patterns of how it works, it becomes easier in the long run. All right, next example is the same area again, but this time we're rotating it around the line x equals 3. So if I can draw this really quick. 1, 2, 3, 1, 2, 3, 4, 5, 6. So again, it's this triangular area. And I'm rotating it around the line x equals 3. So that red line is the line x equals 3. So first thing I want to do is I want to reflect it across that line. So if I reflect it, it looks like this. So if you can imagine that it's being rotated, it looks, again, like kind of like a Hershey's Kiss. It's a solid figure. Notice that it's touching the entire axis of revolution. There's no holes in the middle. So this is an example of a disk. Again, there's no empty gaps on the inside. So we're back to only having the capital R and not the lowercase r, kind of like the very first example. It's a solid figure. It looks like a Hershey's Kiss with straight sides to it. It's been rotated around the line x equals 3. So, again, everything needs to be in terms of y. So we already know this function is x equals 1/2 y. We know our lower limit of integration is y equals 0. We know our upper limit of integration is y equals 6. So if I'm looking for an expression to represent the radius of this circle that I've drawn, I drew it in purple right here. Here's the radius. Again, tilt your head to the right. The top function is 1/2 y. You guys can see that right here, 1/2 y. The bottom function is, oh, I'm sorry. Let me do it the other way. Well, yeah, no, it's not going to, well, technically it works out this way, but that's okay. I'm going to flip it. The reason I'm going to flip it is because I thought this was the y-axis for a minute, but it's not. And actually, that's not the equation x equals 1/2 y. It's the one on the other side. So let me fix that, just because I don't want to confuse you guys. This equation over here is x equals 1/2 y. All right, so when I'm looking at my radius, it's this purple line I'm looking at, just because this is the image of it. I don't really want to get you guys confused looking at the image. I want to look at the original area we were working with from the beginning. So let's look at this piece of it. If I tilt my head to the right, the top of this function is the line x equals 3. So in this case, the top of this is 3, and the bottom function is this function, which is now 1/2 y. So an expression to represent the length of this purple line is 3 minus 1/2 y. That's my capital R, my outside radius. 3, which is this line, minus 1/2 y, which is this line. 3 minus 1/2 y. And again, we do not have a lowercase r because there is no inside radius. Since this is a solid figure, we don't have to worry about having a washer. So when I put this into my volume formula, it's pi times the integral. My lower limit of integration is 0. My upper limit of integration is 6. My radius is 3 minus 1/2 y quantity squared, dy. And again, notice that this is the area of the circle, pi r squared. Pi times the radius squared. My limits of integration are in terms of y. My equations are in terms of y, and my integral is in terms of y. All right, pause the video, put this in your calculator, see what you get. All right, I got 56.549. And the last example we're going to do with this shape before we move on to a different one is this one. So, same shape. Let me draw it one more time. Only this time we're rotating it around the line x equals 4. So here's the line x equals 4. So if I reflect that shape across the line x equals 4, it looks like this. And if I connect it, here's my outside circle, here's my inside circle. So on the outside, I'm trying to think of what this looks like. Let's see, you got a pretty solid figure. You got a pretty solid figure from this like triangular shape that gets rotated around. The inside is a cylinder, so notice the inside has straight walls. So because the inside has straight walls, the inside hole is cut out of this almost like a cylindrical shape. So if I was gonna make up something of what this looks like, here's my best shot at it. To me, this looks like a Hershey's Kiss. Imagine if it was a whole complete Hershey's Kiss. Only the top of it is cut off. And then they stuck a straw through the middle to take out the middle of the Hershey's Kiss. And that's kind of what's left over. So that's the shape I imagine when I see this. I see a Hershey's Kiss that is this solid figure where the top of it was cut off so it doesn't come to a point. And then, like I said, a straw was kind of taken out. So the middle of it is hollow. That's the best I got. I'll be here all week. So to represent the radii, the outside radius, the red one I just drew right here. So again, tilt your head to the right. This top function right here is x equals 4. So the top function is 4. The bottom function, remember, in terms of y, is x equals 1/2 y. So my outside radius is 4 minus 1/2 y. For my inside radius, the green one, I just drew it right here. The top function is 4, and the bottom function is this line right here. And this line right here is the line x equals 3. So it's 4 minus 3. 4 minus 3, which is 1. If I put this into my volume formula, I have pi times the integral. My lower limit of integration is 0. My upper limit of integration is 6. And again, those are all in terms of y, the bottom to the top. My outside radius is 4 minus 1/2 y, quantity squared. My inside radius, and again we're subtracting it because I want to take away that volume that's gone. My inside radius is 1 squared dy. So my limits of integration are in terms of y since I'm revolving around a vertical line. My function is in terms of y because I'm revolving around a vertical line, and my integral is now in terms of y as well. And again, notice where these circle equations came from. Pi times the outside radius squared, and pi times the inside radius squared. That's just the area of these circles that I've drawn. So pause your computer, or pause your movie, and put this in your calculator. Alright, so when I put that in my calculator, I got 113.097 as the volume that represents this revolution. Okay, so here's the formulas I told you we'd come back to again. So for the disk, if you can imagine something that's being rotated that does not have a hollow area on the inside, we call that a disk because we don't need to subtract anything away. And here are the two volume formulas you need to know. For rotating around a horizontal line, so let me write that in here. Oops, too far. This first formula is rotating around a horizontal line. So it's pi times the integral from a to b, where a and b are limits of integration in terms of x. R squared dx, it says if the width of the disk is along the x-axis, or in other words, if you're rotating around a horizontal line. For the second one, it's volume equals pi times c, the integral from c to d, where c and d are limits of integration in terms of y. R squared dy, if the width of the disk is along the y-axis, or in other words, a vertical line. The second one down here is the washer method. So if you have a circular region or on the inside or a hollow region on the inside, then you would use this method. So pi times the integral from a to b of big R squared minus little r squared. Again, this is for a horizontal line. And the second one is for a vertical line, where everything changes to being in terms of y when we rotate around a vertical line. All right, so take a minute if you need to pause the video and copy all of this down into your notes. These are all the formulas you're going to need. So notice that you only use capital R if we don't have any holes or hollow points on the middle, but we use r squared minus little r squared if we have a hollow point in the middle. And if you want to, you can jot down these generalizations as well. It says generalizations that you should probably do every single time. Number 1, draw the function. 2, find the region that we're going to rotate. So far, we've only done one example, so it's been the same region every single time, but we're going to look at some more regions and see how it kind of changes what happens. 3, if it's rotated about the x-axis or horizontal line, then everything should be in terms of x. And 3b, if it's rotated around the y-axis or any other vertical line, everything should be in terms of y, including the limits of integration, the functions, and the integral. 4, if it's a disk problem, you only need to find capital R, meaning there's no hollow points on the inside or anything like that. And then the second part of 4b, if it's a washer problem, find both capital and lowercase r. So you know the inside and outside radius, so you know what to subtract. All right, that's as far as we're going to get today. Do me a favor and make sure that you have all this in your notes, and we'll pick up tomorrow with some more examples and kind of go a little bit faster.